So far, we have presented the theory of thermo-poro-elasticity, and we found the constitutive equation for such a relationship, which is the third equation that we see over here. And in order to do that, we had to add a thermal dilation parameter beta, and of course include temperature in this case, which is delta T, where theta is equal to delta T, and delta T is the temperature minus the initial temperature. And we also saw solutions for steady state analysis. If we want to involve now time into the picture, we need to add a new equation. Adding time into the picture will allow us to solve problems like this one, in which we have an injection of a cold fluid and the rock changes temperature as a function of time and as a function of the injected fluids. But let's first address the variation of temperature with time. In order to take into account that physics, we're going to need a new equation, and this is called the heat diffusivity equation, and it is written as follows. It tells you that the variation of temperature as a function of time is a function of the variation of temperature as a function of space. So this is the Laplacian of the temperature, and those are derivatives, second derivatives as a function of space, proportional to the diffusivity parameter, where all of this is a diffusivity parameter. And in this case, let me write it down. This is the diffusivity, it's actually the thermal diffusivity parameter. And here, for example, we have KT, which is the thermal conductivity. The ρ is density as we have seen before, and Cv is the heat capacity at constant volume. And these are thermal properties of the solid. Only this will tell you and will allow you to solve the heat equation, also known as the Fourier equation. However, in order to couple this with thermo-elasticity, we need to add a second component, which is going to tell us what is the variation of temperature as a function of variation of volumetric strains. And it looks like follows. Here we have the 3K beta times the initial temperature divided the density of the solid times the heat capacity times the variation of the volumetric strain with time. And now with this equation, we're going to be able to tell what is the variation of temperature as a function of time. So let me explain a little bit what this equation is. As we said before, we have heat flow because of gradients of temperature, and this is this first part. However, when we add the part of mechanics, we can also have changes of temperature due to changes in volumetric strain. And probably, this is kind of difficult to see, but I propose you think on the following example. Probably you have done this before, but if you haven't done it, just try to do it. If you have a wire of steel, and if you want to break it, just pulling the wire is going to be very difficult, just to cut that wire by tension. So instead, what you can do is you can bend it back and forth. And that bending back and forth, what it's going to do is going to heat up the wire and is going to lower its tensile strength. The heating is this component. is the variation of strain that causes an increase of temperature that lowers the tensile strength of the material and makes it possible to just cut a piece of steel wire just with your bare hands. So if you've never tried that, please do that. Actually, I'm thinking of doing it myself and recording it with a thermal camera that I also plan to watch a YouTube video and do it myself too. So what we would like to know here is how important is this term and if we really need to consider that. In order to do that, let me do the following. I'm going to assume typical parameters for rock. For example, for the parameter beta, I'm going to assume 10 to the minus 5, 1 over Kelvin. For the parameter of the, okay, this is beta, okay, for the bulk modulus. Let me change this so it looks the same as it does on the top. Beta, okay. All right, this is beta. For the bulk modulus, let's use 10 gigapascals. And for the initial temperature, we'll assume that we are near surface conditions. So here I'm going to use 300 Kelvin. For density, I'm going to use here the density times the heat capacity. I'm just going to use one number, and it's going to be 1.76 times 10 to the 6 joules per meter cube times Kelvin. So if we make this product and divide it by this number, you would obtain that all of these parameters is about 50 degrees Kelvin, which means that, for example, if you were to apply a change in volumetric strain of, let's say, a typical value of 1%, then the product of this number times the volumetric strain will give you more or less a change of temperature of 0.5 Kelvin, degrees Kelvin. So 0.5 degrees Kelvin is about 1 degree Fahrenheit, or it's the same as 0.5 degrees centigrade. So it's actually not much, and that's why usually in geomechanics we'll tend to discard this parameter unless we're dealing with some problems in which there is a rapid deformation. Like, for example, when an earthquake occurs, the increase in temperature in the fault gouge could be high enough that we need to include that term. But in most applications, we don't need to do that. So by solving then now these equations, I can tell what is the variation of temperature as a function of space and time, but I can also tell now what is the variation of stresses as a function of space and time, because I have coupled my equations with the ones that I already had before. And let me show an example of how to solve this. If we want to solve this equation, this is a partial differential equation, and we're going to, for non-trivial cases, we're going to have to adopt a numerical solution. So in my case, what I have done is I have coded this equation together with the elasticity equations that we saw before, and I have used the software FreeFEM in order to do that. Let me find the code. The code is right here, where it's a little bit more complex than what we did before, but it's something that definitely you can do as long as you know how to obtain the variational form of the diffusivity equation. All right, so what we're going to do now is we're going to simulate the cooling of a wellbore, and what we'd like to know is what is the effect of the cooling on the stresses around the wellbore. And here I have a domain of 10 by 10 in which I'm going to have a set of initial stresses, and to that set of initial stresses, as a function of time, I'm going to apply a constant temperature boundary condition at the wellbore that is going to simulate, for example, a wellbore which has a fluid that is going through and it's setting a constant temperature in the wellbore. And here, we have the same step, just a few more things. Definition of the thermal properties. We also have, as before, the mechanical properties. And then we have our finite element spaces, our boundary stresses. Now also we need boundary conditions for temperature. And here is my equation that I use. This is the weak form of the equation. And you see it's a little bit longer, but not that much. And of course now I have temperature boundary conditions now. Okay, so by running this problem, we can obtain the solution. And I have already run this problem, and looking at the solution is not that easy to do in FreeFM itself. So that's why now I have used PeraView in order to solve and to see the solution of this problem a little bit clearer. So this is the domain that I simulated, in which I have stresses in the far field and I have also temperatures in the far field. For example, in this case, I have a stress which is larger in horizontal direction than in vertical direction. Here at the right, we're looking at the tangential stress, sigma theta theta. This is what you see over here. And if I zoom in into the wellbore, we see that we have quite a bit of stress over here, the negative values, compression stress, and in this region we have lower stresses and even getting to the value of tension, something that we would expect from the Kirch solution. This is the initial step. At the beginning, I have a temperature of 100 degrees everywhere, and let me zoom in. I'm going to start showing the time steps solved in the solution, and let me go for the first one. This is the solution after 1000 seconds, which is more or less 16 minutes. And we can see that already, because the boundary condition is set to 50 degrees and everywhere else in the domain was 100, this region starts to cool down. And there is a gradient of temperature from the wellbore to the far field. Let me come back in time. I want you to notice how the stresses change because of the change of temperature. So I go to the next time step, and you see how the area with tensile stresses increases, and also the area of the compression stresses starts to enlarge. That's because the decreased stress in tangential direction, or the hoop stress, around the wellbore. And if I continue varying the temperature and showing the variation of the solution with time, stresses are going to get lower and lower around here until I reach the steady state condition. So let me come back to time 0. Temperature is 100 degrees everywhere. This is the solution of stresses that I have for the wellbore, and as time passes by, changes of stress start to happen due to the cooling of the region near the wellbore. After the initial change happens near the wellbore, the stresses near the wellbore, right next to the wall of the wellbore, they don't change that much anymore. So let me continue the simulation. Well, actually, it's the last time step, but let me run it again. We don't see that much of a change after more or less this time, which is after 1 hour. and temperature continues changing, but it doesn't affect the vicinity of the wellbore that much anymore. So in order to do then this kind of simulation, what you would have to do is to add to the mechanical part now the part of the diffusivity of temperature. All right, this is a couple problem of thermo-elasticity. What happens when you have pore pressure? It's going to be a little bit more complicated. I just remember one more thing that I wanted to do before I go into the next topic, and this is to compare this equation with this equation that we saw before. The equation here on the bottom is the diffusivity equation for pore pressure. And notice how similar it is. In the heat diffusivity equation, we have temperature as a variable that we want to solve. And in the poroelastic equation for pore pressure, we have pore pressure as a variable that we want to solve. Also, we have diffusivity parameters. This one is a hydraulic diffusivity parameter, while this one is a thermal diffusivity parameter. We have the gradients as a function of space. And we have the coupling term, which in poroelasticity, most times it cannot be neglected, but in thermoelasticity, sometimes we could neglect that if we have small strains and small strain rates. So in that case, we could neglect that term. But notice how similar they are. The next step is going to be to solve temperature and pore pressure and solve a problem of thermo-poro-elasticity. And this is the next topic. All right, so let me scroll down a little bit over here. And where's my mouse? Okay, right there. Okay, now we're going to talk about a couple problem. Let me add that because it's very important. This is going to be a couple problem of thermo-poro-elasticity. This one is going to be a little bit more complex than the ones that we saw before. First of all, let's start with the constitutive equations. And let me refer here, we're going to use the constitutive equations in the way that Olivier Cussy does in his book, Mechanics and Physics of Porous Solids. And this is going to be in chapter 4.3. And this is going to recall some of the equations that we used before for poroelasticity, and we're going to add the temperature part. All right. First of all, poroelasticity, we saw that it had three equations. One for the mean stress, in which the mean stress depends on the drain bulk modulus, the volumetric strain, pore pressure through the BO coefficient alpha, and now I'm going to have the additional term, which is going to be the volumetric stress term caused by thermal dilation or contraction. Let's go to the next equation. Shear stresses. Little s, Sij, these are going to be our shear stresses S12, S13, S23. They are going to remain unchanged because we're assuming that we are dealing with an isotropic homogeneous solid, that changes of temperature are not going to cause shear stresses or shear strains. So this one remains the same. The third equation was the equation of change of porosity. And this equation was a function of the volumetric strain and also the pressure within the pore space. And now we're going to add a new term that links the change of porosity due to thermal dilation or contraction. Notice that this it's a new variable, and it's not straightforward to say that the porosity is going to change the same amount that what is going to happen with the solid part. Here in this equation, this parameter beta phi is going to depend on the thermal dilation coefficient of the solid, and is going to be related also to the BO coefficient and the initial porosity. And we're going to have one more term, which is going to be the term of entropy SS. And notice this is different than the previous S that we used. And remember, SS is entropy. And entropy is going to tell us the amount of energy in the form of heat that we have in the solid. And let me write this just to make it clear. And this is going to be our equation for material balance that accounts for the heat. The entropy is going to be equal to the initial entropy plus two more terms that are going to depend on the volumetric strain and also on the pressure of the fluid and on the heat capacity. So together now, these four equations are going to allow me to solve the problem, the coupled problem of thermo-poro-elasticity. These are just the constitutive equations. If further you wanted to solve this problem as a function of time, then you will have to add the diffusivity equations for heat and pore pressure. And you can see that it gets a little bit more complex than what we have seen before. So if you want to see the solution for that, we're not going to cover that in this class, but you can find the solution in Olivier Cousy's book in chapter number 4, or also I recommend a recent paper from Professor Zimmerman and his collaborators, which deals with this problem, and these are the same equation but slightly different. And in this paper you're going to see all the equations that you need to solve that problem. So now we know what all of these are: the betas, the alphas, the bulk modulus. Here also you will find the equations of diffusivity for heat and for pore pressure. And if we go further, you can also see the BO coefficient and things that we know by now, and also an application for geothermal energy. I'll post a link to this paper in the description of the video. And let me see if I forget anything else. I don't think so. I think this is the end of this lecture. And if you wanted to expand this problem to consider variation of temperature as a function of time, then you need the heat diffusivity equation. If you further want to include the variation of pore pressure together with temperature, then you need to use the expanded version for thermo-poro-elasticity.